So we're going to do some more gas laws practice. I highly encourage you to read through the problem and attempt to solve it on your own before you go over the answer with me. I think the hardest part about this section is figuring out which equation to use. So in this one, it says determine the number of moles of gas. So right off the bat, I know I'm looking for N because N is our symbol for moles of gas. In a volume of 2.92 liters, so I'll put a V1 for that. And then now we have a temperature, I'll do a T1 here, and 792 torr. Torr is a pressure, right? So I'll do P1. When you only have ones and you never get to a P2 or a T2, that's oftentimes a really, really strong indication that you should be using the ideal gas law because it doesn't have subscripts. What I went ahead and did, remember from the ideal gas law that the units of the stuff that you plug in have to match the units of R. So we have liters, atmospheres, moles, and Kelvin. So I'm good to go on most of them. The only issue is the pressure. The pressure was given in torr. Using the conversion factor, 1 atmosphere has 760 torr. I figured out my pressure in atmospheres. So PV equals nRT. Just start plugging everything in where it belongs. One thing I've done, embarrassingly enough, is I see this P1 here and I'm always tempted to put it down here. So if it helps, maybe cross that out because this is the P1 now that we actually have to use. Don't grab the old unconverted one. So plugging and chugging. Alrighty, since I'm trying to isolate N right here, I'm going to divide both sides by R times T. Alrighty, now that I got it set up, I would highly encourage you, plug this all into your calculator in one step. However, you're going to need a big set of parentheses on top, and then just put a multiplication sign in the middle, divide it by, and then use another set of parentheses around all your values in the denominator. Let's look at how things are canceling here. So Kelvin will cancel Kelvin, atmospheres with atmospheres, liters with liters, and we're left with the moles. It's all the way on the bottom of a double fraction. So when you have something on the bottom of a double fraction, see there's like a fraction here and a fraction here, then that flips up to the numerator. So we have units of moles. And when I put this into my calculator, I got a very reasonable 0.116 moles. Such a cool problem. It really demonstrates why aerosol canisters and fire just don't mix. Very dangerous situation. So we're given the following information. We're dealing with a 1 liter canister, so we'll label that as V, and we got 2 moles of gas inside that canister. I'll do that as an N. And then they tell us the temperature of the campfire, so we'll do a T there. And then the last part of the problem says, what is the pressure in the container? So we're solving for P. Obviously, with everything we wrote down, we don't have a second set of P's or T's or N's. It looks like it's going to be an ideal gas law problem. What I want to show you here, in this problem, we need to solve for P. So I know everybody has their own ways of doing things, but I really personally feel like it saves me time to manipulate the variables before I start plugging in the numbers. Again, completely up to you if you have your way and it's working. So the 2 V's will cancel. I divided by V on both sides, and now I have pressure equals nRT divided by V. And let me just plug everything in. So N will be 2, and then R is a constant, 0.08206 liters times atmospheres, moles times Kelvin. Also in that numerator, we have temperature. The temperature was given in degrees Celsius, but over here, I converted it to kelvins by adding 273.15. So in here, I'm going to do 1,673.15 Kelvin. And then the volume, it's a 1 liter canister. I know I always talk about units, how important they are. It just really helps me know if I set up the problem correctly or not. So moles will cancel with moles, liters with liters, Kelvin with Kelvin, and we're just left with atms. And it makes sense then because we are solving for pressure. When I plugged all this in my calculator, I got an unbelievably high number. Remember, right now you're at 1 atmosphere of pressure. That's what you're feeling, right? But this says that that can will reach 274.597 atmospheres of pressure. I don't think that's possible. Like, the walls of the canister aren't thick enough to withhold that pressure. It's gonna explode before it gets there. But just to see how dramatic that is. The other thing before I wrap up this problem, we only have 1 sig fig here. The temperature kind of looks like an estimate as well because it's 1400. I mean, it's hard to measure the temperature inside a fire, right? So at the end of the day, we only have 1 sig fig. So the best we can do, again, this is just an estimate to kind of wrap our heads around the magnitude of the pressure. The best we can say is that the pressure inside the canister would reach about 300 atmospheres. I'm going to round up to 1 sig fig. So we have this last problem about radon gas. Radon gas is a product of the decomposition of radioactive uranium. And so when radon gas is produced, it tends to seep into the basements of people's homes. So especially in other areas of the country where basements are more common, it really is a big deal. It's the second leading cause of lung cancer in the United States. And so when homes are sold and purchased in other parts of the country, usually you have to have a radon gas test done before the sale's complete. It's that much of concern. Anyways, I digress. This is a very interesting, noble gas, right? For something that's supposed to be unreactive, it does cause a lot of harm to humans. So we have this 5.0 times 10 to the 17th atom sample. And in part A, it's kind of a throwback problem. Feels good to go back to the beginning of the course a little bit, right? They ask us, what is the mass of this sample in micrograms? So I'm going to start with what they gave me. 5.0 times 10 to the 17th atoms. And those are atoms of radon. And then we can use Avogadro's number, right? So we know that 1 mole of radon, it will contain 6.02 times 10 to the 23rd atoms of radon. We're not there yet. We did successfully get rid of atoms, but we're asked to convert this to mass. So now I need to get rid of the moles. So I'm going to put this on the bottom here. 1 mole of radon. Remember, when you're trying to go from moles to mass, you grab that number from the periodic table. So 222 grams of radon in 1 mole of radon. Almost there. This is a very, very small sample of radon. So they asked us to convert it to micrograms. So I'm going to say 1 gram has 1 times 10 to the 6th micrograms. Remember, micrograms are super, super small. There's a million micrograms or microliters in the base unit. All right, so plug this all in your calculator. Please, please, as we're wrapping up the course, and I know some of you will be moving on to higher chemistry courses, don't forget about the E key. So for instance, even on this first value here, we should be doing 5.0, just the single E, not the exponential E, times 10 to the 17th. So because there's a bunch of numbers going on, I would plug 5.0 times 10 to the 17th times 222 times 1 times 10 to the 6th, put a big set of parentheses or hit enter after you do that, and then divide by Avogadro's number. When I did this, I got a mass of 1.8 times 10 to the second micrograms. And you could also do 180 micrograms. Either way, because we'll get our 2 sig figs that we started with. Alrighty, so in part B, we're asked to figure out how many moles of radon gas are in the sample. Just set up another dimensional analysis, starting with 5.0 times 10 to the 17th radon atoms. And all I need here is Avogadro's number, because from that, 1 mole of radon has 6.02 times 10 to the 23rd radon atoms. So atoms canceled atoms, and I'm just left with moles. And I got 8.305647 times 10 to the negative 7 moles. Way too many sig figs. I wrote those all down because we need that value in the next problem. However, if the problem were to end here, we only have 2 sig figs, so we should say 8.3 times 10 to the negative 7 moles of radon. Alrighty, in part C, we're asked to calculate the volume of this sample to microliters. They do talk about STP, it's standard temperature and pressure. Standard temperature is 0 degrees Celsius and standard pressure is 1 atmosphere. That conversion factor that we talked about the other day, the 22.4 liters per 1 mole of gas, that has the restriction that you're at STP. And so that's why this problem brings it up. So again, we're going to use that along with that, and then we'll be able to go to liters and microliters. So I'll do 8.305647 times 10 to the negative 7 moles. And then we can say 1 mole has 22.4 liters. So moles will cancel moles, and now I'm in liters. Actually, I need to take it a step further. They want it in microliters, right? So 1 liter has 1 times 10 to the 6th microliters. When I multiplied across, I got 18.6 microliters, which because of the 2 sig figs, I would report as 19 microliters.